So we have the Maclaurin series expansion for sine x, and here it is. Now, let's suppose that we want the Maclaurin expansion for sine x squared. Now, you could go back and start over from scratch and start generating the derivatives, plugging in the zero. In other words, use the power series expansion for the general function and derive it for sine x squared. But that would be quite the task. And it would be needless if we already have the expansion for sine x. Just plug in an x squared in place of x. So the expansion would look like this. We would have negative 1 to the n, x squared to the 2n plus 1, and then 2n plus 1 factorial here. So that looks like it's going to be much easier than starting from scratch, and we're still going from n equals 0 to infinity. So let's see what this is going to look like then. We've got the integral the summation n for n from 0 to infinity, negative 1 to the n, and then this is going to be x to the 4n plus 2. Yeah, so then we've got 2n plus 1 factorial. And there's our expansion for sine x squared. So let's look at the first few of these terms. If n is 0, let's see what we have. So I'll say, okay, the first term, I just replace the n with 0, and it looks like we have x squared would be the first term. That makes sense since the usual first term is um, x. Okay. Now let's look at the next term. The next term was n equals 1. So we've got 4, 5, 6. So we got minus x to the 6th over 6 factorial. Well, no, not 6 factorial. If n is 1, we've got 3 factorial. You got to be careful. And then the next term, we're alternating here. If n is 2, we've got x to the 10th. And then down in the bottom, we've got 5 factorial. So notice the bottoms are the same. Nothing's changed there. So our next term would have 7 factorial on the bottom, but now we're up to 3. So this is 12, 13, 14, x to the 14th over 7 factorial, and it just goes on and on. So what we have there is the Maclaurin series for sine x squared, and all we did was we built on the work we already did to develop the Maclaurin series for sine x. So here's what we have. We have the Maclaurin series for sine x squared. Now, let's see something really cool we can do with this. Let's suppose that we want to find this integral, the integral from 0 to 1 of sine x squared. Now, of course, if this were just sine x, no problem, we could find the antiderivative, but it's not. It's sine x squared. And we don't know how to find the antiderivative for that one. However, we know the Maclaurin series for sine x squared, and we know that series is just a polynomial. It's an infinite polynomial. It goes on forever, but nevertheless a polynomial, and we can find the antiderivative of a polynomial. So we think about it this way. Now the argument for not doing this for not using the Maclaurin series is that it's infinite. And we would be finding finding antiderivatives for an infinitely many terms. However, what if we agree that there is a error that we're willing to tolerate? Let's suppose that we're willing to tolerate an error of let's say 0.0001, as long as the difference between the actual integral and our estimate is no bigger than 0.0001. Let's suppose we can live with that. Well, notice that this is an alternating series, and we know how to find the maximum error for a particular alternating series. So let's proceed that way. Here we have this integral, and let's think about just finding the antiderivatives for these terms right here. And actually, I'll do it for the summation as well. First of all, for the summation, you notice we'll just use the power rule for integration. We take the x to the 4n plus 1, that would be 4n plus 3, right? I just add 1, and then I divide it by 4n plus 3, and we've already got the 2n plus 1 factorial. Okay, so, and this is n goes from 0 to infinity. Okay, so all I did was I just, you know, used the power rule for integration for the summation. Now, let's look at the terms, what the terms would look like for this. Well, the first term would be, you know, we've got x squared, so this is going to be 1 over 3 x cubed. That would be the very first term. In other words, that's when n equals 0. Now let's see if that works out. I got that from just looking at this x squared. Let's see if this works out. If I put a 0 in for n, the top is just going to be x cubed. Okay, so far so good. What about the bottom? If I put a 0 in for n, I get 3. Yeah, so it works. Now let's look at the next term, this one right here. I'm going to add 1 to the 6th and divide by that. So let's see what we've got. We've got 7 times 3 factorial x to the 7th. And that's the next term. And let's see if that works out for us. If n is equal to 1 on the bottom, we've got, let's see here, 4 plus 3. Yeah, that's 7 times, and this one is 3 factorial. Yeah, and on the top, if we put in the 2 or the 1, we have 7. Yeah, so that works out. Yeah, so it looks like our summation here is, you know, consistent with just integrating term by term over here. So now let's look at this one. Next one, we've got x to the 11th over uh, 11 times 5 factorial. Okay, and then let's look at this one. Minus x to the 15th over uh, 15 times 7 factorial. Okay, now we could go on and on with this, but what we have here is we have the antiderivative. This is the antiderivative of sine x squared for the first 4 terms here. Now, I'm going to use the fundamental theorem of calculus. I'm going to plug in a 1 and then subtract off plugging in a 0. Well, if I plug in a 1, look what you have. You just have 1/3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial minus 1 over 15 times 7 factorial. Because notice, you plug in a 1 for the x, and then you subtract off plugging in a 0 for the x. Well, if I plug in a 0 for the x, all those terms are 0. So really, this is the alternating series that I'm looking at. And what I want to do, I want to find which one of those terms gives me a value less than 0.0001, less than or equal to that. I want to find out which term gives me that. So what I do is I just get my calculator and I calculate away. So if I get to this first term here, I go 1 divided by 7 times 3 factorial. And that gives me about a 0.85. Okay. So that's not what I'm looking. Whoops, no, doesn't give me 0.85. I left off. Let me see. I left off a parentheses. Divide it by 7 times 3 factorial. And that gives me 0.02. Sorry about that. Approximately. I'm just rounding here. It's certainly not less than 0.0001. Now, if I go to the next one, I go 1 divided by 11 times 5 factorial. And that's going to give me approximately 0.0007. Not quite there, right? Because I need 0.0001. So let's go to this next one. I take 1, divide it by, there goes 15 times 7 factorial. I'm just punching it into my calculator. Oh, here's what I get. I get point. Let's see here. 1, 2, 3, 4, 1, approximately. Ah, that's it. Notice this is indeed less than this. So this right here is my error. So if I want to approximate that integral, here's what I'm going to do. I'm going to take this, whoops. Here's what I'm going to do. I'm going to integrate from 0 to, so this is what it looks like. This is approximately equal to this thing. The integral from n equals 0 to, let's see here, I got the first, second, third term. So this would be n equals 0 to 2. And remember, it's -1. Let's see here. Let's go back. It's this thing right here. -1 to the n, 4n plus 3, x to the 4n plus 3. Whoops, not x. Yeah, like that. See, because I just put a 1 in for the x. And we're going from n equals 0, 1, and 2. And then this right here, the next term, when n equals 3, that's the error term. So this right here, this sum is an approximation for this integral. And that approximation we know is less than 0.0001.